Hello everyone, my name is Farhang Salari. Today we want to talk about retaining wall concept and how you can do the manual calculation for the acting force if you don't access to any software or to the geotechnical report. In generally speaking, retaining walls are structures that support backfill and allow for a change of grade. It means that the height of the retaining wall can be varies from 2 to 3 feet to sometimes 30 feet. For instance, a retaining wall can be used to retain fill along a slope, or it can be used to support a cut into a slope. Retaining wall structures can be gravity type structures, semi-gravity type structures, cantilever, and sometimes restraint. Prior to completing any retaining wall design, it is first necessary to calculate the forces acting on the wall. There are three categories of lateral earth pressure, and each depends upon the movement experienced by the vertical wall on which the pressure is acting. The three categories are at-rest earth pressure, active earth pressure, and finally passive earth pressure. The at-rest pressure develops when the wall experiences no pressure or lateral movement. This typically occurs when the wall is restrained from movement, such as a long basement wall that is restrained at the bottom by a slab and at the top by a floor framing system, prior to placing soil backfill against the wall. The active pressure develops when the wall is free to move outwards, such as a typical retaining wall, and the soil mass stretches sufficiently to mobilize its shear strength. On the other hand, if the wall moves into the soil, then the soil mass is compressed, which also mobilizes its shear strength, and the passive develops. Lateral earth pressure is related to the vertical earth pressure by coefficients termed the at-rest earth pressure coefficients, active earth pressure coefficients, and passive earth pressure coefficients. The lateral earth pressure is equal to vertical earth pressure times the appropriate earth pressure coefficient. Depending upon whether the soil is loose sand, dense sand, normally consolidated clay, or over consolidated clay, there are published relationships that depend upon the source engineering values for calculating the at-rest earth pressure coefficient. One common earth pressure coefficient for the at-rest condition in granular soil is K equal 1 minus sinus phi, where K is the at-rest pressure coefficient and phi is the soil friction value. Active and passive coefficients. When discussing active and passive lateral earth pressure, there are two relative simple classical theories that are widely used: Rankine earth pressure theory and Coulomb earth pressure theory. But what's the difference? Under Rankine, there is no adhesion or friction between the wall and soil. Lateral pressure is limited to vertical wall. Failure occurs as a sliding wedge along an assumed failure plane defined by phi. And also lateral pressure varies linearly with depth, and the resultant pressure is located 1/3 of the height above the base of the wall. And finally, the resultant force is parallel to the backfill surface. But on the Coulomb theory, lateral pressure is not limited to the vertical walls. And also, the resultant force is not necessarily parallel to the backfill surface because of the soil wall friction value. And there is a friction between wall and soil, and takes this into account by using a soil wall friction angle. So we note that in this course only Rankine theory is considered because the Coulomb theory is derived from a more complicated expressions that depends on the angle of the back of the wall, the soil wall friction value, and the angle of backfill. The Rankins active and passive air shear coefficients, you can see the formula and the above table, some common degree or phi for 28, 30 and 32 that most of the case the behavior of the soil will be like this. The coefficients for the active and for the passive is calculated and you can use it. Now how to do the calculating the vertical effective overbended pressure. The vertical effective overbended pressure is the effective weight of soil above the point under consideration. The term effective means that the submerged unit weight of soil is used when calculating the pressure below the groundwater level. For instance, assume that the soil has a total unit weight of 120 PCF or pounds cubic foot and the groundwater level is 5 feet below the ground surface. The vertical effective overbending pressure at the depth of 10 feet below the ground surface or 5 feet below the groundwater depth will be calculated by this formula. 5 times gamma plus 5 times gamma prime. The gamma is the total unit weight of the soil and gamma prime is the effective or submerged unit weight of the soil, which equals the total unit weight of the soil minus the unit weight of the water. Thus, if you replace those values on the formula, the answer will be 888 PSF or pound square foot. There is a relationship between the vertical effective overbended pressure and the lateral air pressure. The lateral air pressure at the point below ground surface will calculate by this formula, where the vertical effective overbended pressure and those simple relatively reference to active and passive air pressure. The total lateral air pressure force is the area of the pressure diagram along the wall. In the example shown later in this course, the area of the air pressure diagram is the lateral air pressure of the bottom of the wall that gamma h is the vertical effective overbending pressure in this example times the height of the wall times 1.5 since the pressure distribution increased linearly with depth creating a triangular shape. Thus, the total active air pressure force acting along the back of the wall is the area of the pressure diagram expressed in below. And the total passive pressure force will be calculated the same as active. And the total force acts along the back of the wall at the height of h divided by 3 from the base of the wall. So here, this one, air pressure force equal half of the coefficients of the active times by the unit weight of the soil and the height powered by 2. And the same for the passive. Aside from the air pressure force acting on the wall, other forces might also act on the wall, and these are superimposed onto the air pressure force. For example, these forces might include surcharge load, earthquake load, water pressure, and the compaction. For the surcharge load, a surcharge load results from forces that are applied along the surface of the backfill behind the wall. These forces apply an additional lateral force along the back of the wall. Surcharge pressure results from loads such as line load, strip load, embankments, and traffic, such as a parking lot. Floor loads and temporary loads such as the construction traffic and other material. Generally, elastic theory is used to determine the lateral pressure due to the surcharge, and solutions are available. For the earthquake force, additional lateral loads resulting from an earthquake are also superimposed onto the lateral earth pressure where required. Publications such as AASHTO standard specifications for highway bridges and other textbooks provided methods for calculating the earthquake forces can be used. For water pressure, walls are typically designed to prevent hydrostatic pressure from the developing behind the wall. Therefore, the laws applied to most walls will not include water pressure. In case where hydrostatic water pressure might develop behind an undrained wall, the additional force resulting from the water pressure must be superimposed onto the lateral earth pressure. Since water pressure is equal in all directions, the water pressure distribution increases linearly with the depths, and the weight of the water can be considered as 62.4 PCF or pound cubic force. And finally, for the compaction, if heavy rollers are used to compact soil adjacent on wall, then high resident pressure can develop against the wall, increasing the total pressure. Also, a reasonable amount of backfill compaction is necessary. Excess compaction must be avoided. The other parameter is the sliding. A retaining structure has a tendency to move away from the backfill surface because of the horizontal driving forces resulting from the soil backfill and other forces such as surcharge. Generally, the wall resists sliding, but the frictional resistance develops between the foundation of the wall and the foundation soil. Also, other horizontal forces act opposite to the driving force, such as passive soil pressure in the field in front of the wall. It is often ignored. The factors of safety with respect to sliding equals the resisting force divided by the driving force. A minimum factor of safety of 1.5 is desirable to resist sliding, assuming that passive resistance from any field in front of the wall is ignored. This is common assumptions and avoids relying on the presence of soil in front of the wall for additional resistance. And that is the formula that sliding is equal sigma v tangent k phi times by 1 divided by earth pressure. So sigma v is the total vertical force, and the earth pressure is a horizontal active earth pressure force, and the tangent k phi is the coefficient of friction between the base of the wall and the soil. And the factor K ranges from half to 2/3, and phi1 is the friction angle of the foundation soil. And finally, for the overturning, the horizontal pressure on the backfill side will push the wall outward, which will tend to overturn around the end of the toe. The overturning moment is the sum of the horizontal forces times the distance to the footing base. This overturning moment must be resisted by an opposite moment produced by the sum of the vertical forces times the distance to the toe end, including the wall self-weight and the weight of the back wheel over the heel and toe. The factor of safety against overturning is defined as the restraining moment divided by the overturning moment, and the minimum value should be 1.5. So in our first example, use the ranking method to calculate the total active lateral force and location of the force behind the 10-foot height vertical wall. Assume that the soil has a total unit weight of 120 pound cubic foot and the friction value of 32 degrees. Assume that there is a uniform surcharge of 100 pound square foot located along the surface behind the wall. Groundwater is well below the depth of the foundation so that groundwater pressure does not develop behind the wall. And you see on the shape that the wall height is 10. So let's go and do the calculation. So the solution is the coefficients for the active is 1 minus sinus phi. The phi was 32. So if you replace the 32 on the formula, the answer for the coefficients active is 0.307 is the active air pressure coefficients. At the bottom wall or surcharge pressure is equal coefficients times by the surcharge. So we just assume that the surcharge is 100, so it will be 30.7 psf. And also at bottom of wall, active lateral air pressure is equal coefficients times by the unit weight of the soil times by the height. So if you replace those values, the answer will be 368.4 psf. And finally, the total surcharge force, if you replace on the formula, will be 307 pounds and act at the height of half of the height from the base of the wall. Total air pressure force is equal half of the coefficients times by the unit weight of the soil times by the height of the wall power 2. So if you replace those values, the answer will be 1842 pounds and act at the height of h divided by 3 or on the third of the wall from the base of the wall. So the total active force will be 2149 pounds for this example. In the second example, using the ranking methods of analysis, calculate the factors of safety with respect to sliding, overturning, and bearing capacity. Use the values presented in the following table. It is inferred that all calculations relate to a unit length of the wall. So we can see that the depth of the footing is 12 inch and the total height is 9 feet and the width is 6 feet. And we know that the friction angle is 32, soil backfill unit is 125, friction angle of the foundation soil is 33, Rankine active pressure coefficients is 0.307, concrete unit weight 150 pcf, dimension of the concrete wall section 1, 2, 3. So if you just focus on the photo, you can see that that is the section 1, that is the section 2, and that is for section 3, and we have the dimensions of those sections. So for the solution, first we need to calculate the air pressure force. So if you replace those values from the table, the answer will be 1554.2 pounds. And once you want to do the calculation for the moment is the air pressure times by the height. So here you calculate the air pressures times by the height that or the arm. Your arm will be 3 for this scenario, and the answer is 4662.6 foot per pound. And if you want to do the calculation for overturning, the overturning calculations. If you want to follow this formula, here you have the table. For the section 1 you have the area, section 2 you have the area, and section 3 you have the area. You know the unit weight of the concrete and you know the unit weight of the wall, because section 1 and section 3 was wall and footing, so we have concrete, and on section 2 we have the soil on the right of the wall, so the unit weight of the soil was as sum as 125. And then you can calculate the weight very easily, and the sum of all the weights or the shear will be 6100. And if you times those value by the R, that very easily you can figure them from this photo regarding the R. The moment will be calculated and you can have the sigma of your moment here. And if you replace, you will have the overturning factor. And if you remember, we mentioned that the overturning factor need to be more than 1.5, so that is good here. And for the sliding, if you just put those values that we did the calculation and replace on the formula, it need to be more than 1.5, that again it happened. And also we have the other calculation to see if the bearing capacity is okay or not okay. So here we just assume that if our bearing capacity of the soil be 5000 psf, first you need to do the calculation for the eccentricity, and B is for the width. The width of the footing was 6 feet, and if you replace the other parameter on the moment that we did the calculation, it is 0.4. And then you have to optimize the Q max and the Q mean. So if you use this formula and replace the values, you can figure out that the max Q will be 1423.4, and if you replace on this formula, your answer is 3.5, and normally for the bearing capacity is recommended to be more than 2. That is good again. So the material presented in this course is intended only for general familiarizations with the subject matter and a better understanding. The course does not cover all aspects of the subject. I hope this video be useful for your understanding. If you have any questions, please add a comment for me, and if you think this video is useful, please do not forget to subscribe. Thank you.